Press your hand against a table and feel the resistance, the firmness, the undeniable presence of something solid pushing back against your skin. That sensation has guided human intuition since the earliest days of our species, convincing us that solid things resist us, that they have substance, that they are real in a way we can feel. What if that feeling is a magnificent deception? The table exists, your hand exists, and the resistance you feel is completely real. But here is the thing. The mechanism producing that sensation bears no resemblance to what your intuition suggests. Nothing is touching in any traditional sense. No surface presses against another surface. Objects you perceive as solid are, by volume, almost entirely empty. This is not philosophy or metaphor, but the measured, verified, experimentally confirmed reality of matter at its fundamental level. Every atom composing your body, the air filling your lungs, the chair beneath you, and the planet under your feet, consists of nearly nothing at all, held together and given the illusion of solidity by forces and quantum rules operating on scales far below anything your senses can detect. By the end of this video, you will understand what solidity actually is and why it feels so convincing, despite being, in the strictest physical sense, an illusion. You will learn what happens when two objects appear to touch and why actual contact never occurs. You will discover the quantum principle preventing matter from collapsing while giving everything its apparent rigidity. And you will see how an experiment over a century ago revealed that atoms are almost entirely empty space. If you find this kind of deep exploration valuable, consider subscribing, as it helps this channel continue diving into questions that reshape how we understand reality. Now, let us begin. Start with the fundamental question: what is solidity? And when you experience something as solid, what is actually happening at the atomic level? Two mechanisms work together here, and neither has anything to do with physical objects making contact the way you might imagine. Electromagnetic force accounts for the first mechanism. Every atom consists of a positively charged nucleus surrounded by negatively charged electrons. And when two atoms approach each other, their electron clouds begin interacting. Negative charges repel each other, and this repulsion creates resistance, a force pushing back against anything trying to bring those atoms closer together. The second mechanism carries the name Pauli Exclusion Principle, after physicist Wolfgang Pauli, who proposed it in 1925. This quantum mechanical rule states that no two identical fermions can occupy the same quantum state simultaneously. Electrons are fermions, and when electron clouds of different atoms start to overlap, this principle kicks in with tremendous force because the electrons cannot simply occupy the same space in the same way. They resist overlap with a strength that physicists call Pauli repulsion. Together, electromagnetic repulsion and Pauli exclusion generate the sensation you experience as solidity. When your hand presses against a table, electron clouds of atoms in your hand are being pushed back by electromagnetic forces from electron clouds in the table, amplified by the quantum resistance of the Pauli principle. Nothing touches in any traditional sense, but forces interact, and those forces are powerful enough to stop your hand completely. I remember the first time this truly sank in for me. The table was not pushing back because it was solid, but was behaving as if solid because invisible forces were pushing back. Solidity was the effect, not the cause. Understanding this requires travelling back to a laboratory in Manchester, England between 1909 and 1911. Ernest Rutherford, working alongside Hans Geiger and Ernest Marsden, conducted what became known as the gold foil experiment. They fired alpha particles, which are positively charged helium nuclei, at an extremely thin sheet of gold foil, while observing where those particles ended up after passing through or bouncing off. The prevailing model at the time, called the plum pudding model, came from J.J. Thomson, who had discovered the electron in 1897. Thomson proposed that atoms were uniform spheres of positive charge with electrons embedded throughout, like raisins in a pudding, which meant alpha particles should pass through with only minor deflections, since the positive charge would be spread out and weak. What Rutherford's team observed was startling. Most alpha particles passed straight through as expected, but some deflected at large angles, and roughly 1 in 8,000 bounced straight back toward the source, deflecting by more than 90 degrees. Rutherford later described his astonishment by saying it was as if you fired an artillery shell at tissue paper and the shell came back and hit you. Something dense and concentrated had to be responsible for completely reversing a fast-moving alpha particle. His conclusion, published in 1911, proposed the nuclear model. Positive charge and nearly all atomic mass concentrate in a tiny central nucleus, while electrons orbit at much greater distances, leaving most of the atomic volume empty. Alpha particles passing far from any nucleus continue unimpeded. Those passing close experience strong electromagnetic repulsion and deflect sharply, and those headed directly at a nucleus get completely reversed. The mathematics worked beautifully, with Rutherford's formula predicting the angular distribution of scattered particles and matching observations precisely. This experiment demonstrated something unsettling. The solid gold foil, dense and opaque to human senses, was, at the atomic level, mostly empty space, through which particles could pass unobstructed. The scale of this emptiness exceeds anything in ordinary human experience. A typical atom measures approximately 10 to the negative 10 meters in diameter, about 0.1 nanometers, roughly 3.94 times 10 to the negative 9 inches, which works out to about 4 billionths of an inch. Already impossibly small by everyday standards, yet the nucleus within that atom is far smaller still, measuring approximately 10 to the negative 15 meters across, about 1 femtometer, roughly 3.94 times 10 to the negative 14 inches. The ratio between these two sizes is staggering. The nucleus is about 100,000 times smaller in diameter than the atom containing it. Volume scales as diameter cubed, so the nucleus occupies only about 10 to the negative 15 of the atom's volume, 1 quadrillionth, which means atoms are approximately 99.99% empty by volume, 15 nines after the decimal point. Analogies help bring these numbers into focus. Picture expanding an atom to the size of a football stadium, 100 meters or about 328 feet across. And at this scale, the nucleus at the atom's center would measure approximately 1 millimeter in diameter, about 0.039 inches, roughly the thickness of a credit card edge. A single tiny bead sitting at the center of an entire football stadium, with nothing else occupying that vast space except invisible fields and probability clouds. Another visualization. Enlarge the nucleus to the size of a marble, about 1 centimeter or 0.39 inches across, and the surrounding atom would expand to approximately 1 kilometer in diameter, about 0.62 miles. A marble at the center of a sphere stretching more than half a mile in every direction. An important nuance deserves attention here. When physicists say atoms are mostly empty, they do not mean the space between nucleus and electrons is truly nothing. That space is filled with electromagnetic fields and quantum wave functions, probability distributions describing where electrons might be found. The emptiness is real in the sense that no solid substance fills the space, but misleading if you imagine complete absence of anything physical. If atoms are mostly empty space, why does anything feel solid at all? And why does your hand not simply pass through the table, electrons sliding through gaps between distant nuclei? The answer lies in the extraordinary strength of electromagnetic forces at atomic scales. Gravity dominates our everyday experience, keeping planets in orbit, holding us to Earth's surface, shaping the large-scale structure of the cosmos. And we think of it as a powerful force because we experience its effects constantly. At atomic scales, gravity becomes negligible because electromagnetic forces completely overwhelm it. Using values from NIST code data, the ratio of electromagnetic force to gravitational force between an electron and a proton runs approximately 2.3 times 10 to the 39, which is 2.3 followed by 39 zeros. For 2 electrons, the ratio climbs even higher to approximately 4.2 times 10 to the 42. These ratios do not depend on distance, because both electromagnetic and gravitational forces follow inverse square laws, decreasing with the square of separation. Electromagnetic force remains stronger than gravity by the same factor, whether particles are close or far apart. This explains how contact forces can be so strong without any physical interlocking at the microscopic level. When you press your hand against a table, electromagnetic repulsion between electron clouds does all the work, while gravity contributes nothing meaningful to that resistance. The forces preventing your hand from passing through are 10 to the 39 times stronger than gravitational attraction between those same particles. The solidity you feel is electromagnetic solidity, having nothing to do with hard objects colliding and everything to do with charged particles repelling each other across empty space. The Pauli Exclusion Principle deserves deeper examination because its role in creating solidity is often underappreciated. Pauli introduced this principle to explain patterns in atomic spectra that existing theory could not account for. Why did electrons in atoms arrange themselves in shells? And why did certain configurations appear forbidden? Electrons, being fermions, could not share the same quantum state. A quantum state is defined by quantum numbers, describing properties like energy level, orbital shape, orbital orientation, and spin. Two electrons can occupy the same energy level and orbital only if they have opposite spins. And once both spin states are filled, no additional electrons can enter that orbital. They must occupy higher energy states instead. This explains the entire periodic table of elements. Helium has 2 electrons in its innermost shell and no more, because that shell contains only one orbital holding 2 electrons with opposite spins. Carbon forms 4 bonds because it has 4 electrons available for bonding and 4 orbitals to accept electrons from other atoms. Oxygen forms 2 bonds for similar reasons. The periodic organization emerges directly from how Pauli exclusion constrains electron configurations. When atoms are pushed together, electron clouds begin overlapping, and electrons from one atom start occupying the same region of space as electrons from another. Pauli exclusion forbids them from all dropping into the same low-energy quantum state. So some electrons are forced into higher energy states, which costs energy and manifests as resistance to compression. In extreme environments like white dwarf stars, this effect becomes the primary support against gravitational collapse, a phenomenon called degeneracy pressure. Matter in a white dwarf is packed so tightly that electromagnetic repulsion alone cannot support it. Yet what holds it up is Pauli exclusion, electrons refusing to share quantum states despite enormous gravitational pressure forcing them together. Neutron stars take this further, with electron degeneracy overcome and neutron degeneracy providing support, where a teaspoon of material would weigh hundreds of millions of tons. The same principle operating in everyday matter gives it structural rigidity. You cannot squeeze a rock into half its volume because doing so would force electrons into quantum states they are forbidden from occupying. Quantum field theory provides an even more fundamental perspective on why matter is not what intuition suggests. Classical physics imagined particles as tiny objects, little spheres or points with definite positions moving through empty space. Quantum mechanics complicated this picture with wave functions and uncertainty. But quantum field theory goes further still. The fundamental entities in this framework are not particles at all, but fields permeating all of space. The electromagnetic field, the electron field, fields for quarks, for neutrinos, for every type of fundamental particle. What we call a particle is, in this picture, an excitation of its corresponding field. An electron is not a tiny ball floating through space, but a localized disturbance in the electron field, a ripple in something extending everywhere. When you detect an electron at a particular location, you are detecting where that field excitation concentrates at that moment. This reframing matters for understanding solidity. If particles were truly tiny, hard spheres, then matter, being mostly empty space, would be surprising but conceptually simple. Hard things separated by nothing. The reality differs because there are no hard things, only field excitations, wave functions spread across space. probability distributions, describing where measurements might find energy concentrated. Before measurement, an electron does not have a definite position. It exists as probability, spread across an orbital with varying density. The wave function encodes where you are likely to find the electron if you look. But until you look, the electron is not there or anywhere, existing instead in superposition of possibilities. When you touch a table, are not experiencing tiny hard balls pressing against each other, but quantum field excitations interacting through electromagnetic forces, governed by rules like the Pauli Exclusion Principle. The entire picture of solid objects, built from solid particles, is a useful approximation, breaking down completely at fundamental scales. For most of the 20th century, ideas about atomic structure remained somewhat theoretical. Scientists knew atoms were mostly empty because of Rutherford's experiment and subsequent measurements. And they knew the Pauli Exclusion Principle governed electron behavior because it explained spectra and chemistry. But directly measuring the forces involved at atomic scales remained beyond reach. That changed with the development of atomic force microscopy, particularly high-resolution techniques refined in the 2000s and 2010s. Atomic force microscopy, or AFM, works by scanning an extremely sharp tip across a surface while the tip attaches to a tiny cantilever, bending in response to forces between tip and surface. Measuring how much the cantilever bends at each position allows researchers to map surfaces with atomic scale resolution. As AFM resolution improved, researchers could probe actual forces at work when atoms approach each other. High-resolution AFM studies have explicitly connected the repulsive forces observed at very short ranges to Pauli repulsion, the resistance arising from electron cloud overlap governed by the exclusion principle. IBM researchers working on advanced AFM techniques described how contrast in their images, the bright and dark patterns revealing molecular structure, directly reflects this Pauli repulsion. When the scanning tip approaches too closely, electron clouds of tip and surface begin overlapping, and quantum mechanical resistance kicks in, creating the force that produces the image. These experiments provide direct observational confirmation of something previously inferred from indirect evidence. The sensation of solidity, scaled down to atomic dimensions, arises from electromagnetic forces and Pauli exclusion, exactly as theory predicts. The abstraction becomes concrete, and we can watch atoms repel each other while measuring the forces involved. This distinguishes scientific understanding from philosophical speculation. The claim that solidity is an illusion rests not on argument alone, but on measurements, on experiments, on predictions matching observations. Scanning tunneling microscopes work by measuring tunneling current between an extremely sharp tip and a surface. Because tunneling current depends exponentially on distance, tiny changes in separation produce large changes in current. This sensitivity allows imaging surfaces with atomic resolution, revealing individual atoms as bumps in the landscape. These microscopes exploit quantum tunneling, where particles pass through barriers they classically should not penetrate. The fact that quantum effects allow such precise imaging of individual atoms reinforces how different the quantum picture is from the classical one. Matter viewed at these scales looks nothing like solid continuous substance. Transistors in modern electronics have shrunk to nanometer scales, where quantum effects, including tunneling, become increasingly important. Engineers now design devices deliberately exploiting quantum phenomena rather than treating them as nuisances. The quantum nature of matter, once an abstract concern of physicists, has become an engineering constraint and opportunity. From a solidity perspective, tunneling is striking. A classical solid barrier absolutely stops a classical solid particle. A quantum barrier is probabilistic. Particles can and do pass through with calculable probability. Apparent impenetrability of solid matter has quantum exceptions. Nothing is absolutely impenetrable when particles are described by wave functions rather than definite positions. Every physical action you perform relies on the same underlying physics. The apparent contact, the solid grip on reality, is always electromagnetic interaction across gaps that, relative to atomic dimensions, are vast. The world works as if solid, because electromagnetic forces are so strong and consistent that the illusion is perfect at human scales. Extreme environments reveal these principles in dramatic fashion. In white dwarf stars, matter has been compressed far beyond normal densities. A teaspoon of white dwarf material would weigh tons. Electromagnetic repulsion has been overcome by gravitational pressure. What prevents further collapse is degeneracy pressure from Pauli Exclusion Principle. Electrons, forbidden from sharing quantum states, resist compression with force balancing gravity itself. The star exists in a state that electromagnetic forces alone could not maintain. In neutron stars, even electron degeneracy pressure has been overcome. Electrons and protons have been squeezed together to form neutrons. And now, neutron degeneracy pressure, the same Pauli principle applied to neutrons, holds the star up. Density is mind-bending. A teaspoon of material would weigh hundreds of millions of tons. These exotic objects demonstrate that rules governing ordinary solidity have limits. Push hard enough and electromagnetic repulsion fails. Push harder and electron degeneracy fails. At each stage, different physics takes over. The smooth progression from solid to collapsed object follows directly from principles we have been discussing, taken to their extremes. In ordinary matter, you never approach these limits. Forces involved are strong enough that everyday pressures cannot overcome them. A hydraulic press crushing a car is nowhere close to overcoming Pauli exclusion. Compressed metal remains solid, its electron clouds merely squeezed closer, atoms maintaining integrity despite deformation. This robustness is itself remarkable. The illusion of solidity is extraordinarily stable. You can heat matter, cool it, stretch it, compress it, and, within wide limits, the same electromagnetic and quantum forces continue producing the same sensation of solid resistance. The illusion adapts but persists. Carbon, under immense pressure, rearranges from graphite to diamond. Same atoms, same element, but forces push them into different configuration with different bonding. Laboratory experiments have achieved pressures high enough to metallize hydrogen, forcing the normally gaseous element into a state where electrons become delocalized, like in metal. These extreme conditions do not create new matter. they force existing matter into new configurations of the same underlying forces and quantum rules. Pressure at Earth's center compresses iron into dense core. Forces involved dwarf anything we encounter at the surface. Yet even there, the physics remains the same. Electromagnetic forces between electron clouds, constrained by quantum exclusion, creating stable structures at whatever density gravitational pressure dictates. Temperature adds another dimension to understanding solidity. What we perceive as temperature is, at the atomic level, motion. Atoms in a solid are not stationary, but vibrate around fixed positions, jiggling back and forth within the constraints of bonds holding them in place. Higher temperature means faster vibration and more kinetic energy distributed among atoms. This vibration might seem to conflict with solidity, because if atoms are constantly moving, how can matter feel stable? Vibrations are small compared to atomic spacing and fast compared to our perception. Your senses average over billions of vibrating atoms and countless oscillations per second, perceiving smooth, stable matter where rapid microscopic motion occurs. Heat a solid and vibrations intensify. Atoms swing farther from equilibrium positions. Add enough heat, and bonds can no longer constrain the motion, so atoms break free and begin moving around each other. The solid melts into liquid. Solid to liquid represents a transition in the illusion's nature. In solids, atoms vibrate in place, with average positions fixed in a lattice, producing macroscopic rigidity. In liquids, atoms move freely past each other, with positions constantly changing, producing macroscopic flow. Neither state involves contact in the traditional sense. Both are configurations of electromagnetic forces and quantum constraints, differing only in how much constraints restrict atomic motion. Heat a liquid further, and atoms gain enough energy to escape each other entirely, forming gas. The illusion of continuous substance breaks down as gas fills its container without maintaining shape or volume independently. Atoms fly freely, colliding and bouncing, but not held in fixed relationship. Yet even in gas, each collision remains electromagnetic interaction, electrons repelling electrons, forces without contact. Different molecular bonds create different manifestations of the solidity illusion. Covalent bonds, where atoms share electrons, produce the strongest structures. Diamonds are held together by covalent bonds between carbon atoms, each carbon sharing electrons with 4 neighbors in a rigid 3-dimensional lattice. That legendary hardness and resistance to scratching arises from the strength of shared electron bonds. Yet, even diamond is mostly empty space. Its hardness purely a matter of how strongly electromagnetic forces and quantum exclusion effects resist deformation. Ionic bonds form when electrons transfer completely from one atom to another. Table salt consists of sodium atoms that have lost an electron and chlorine atoms that have gained one. The resulting ions carry opposite charges, and electrostatic attraction holds them in crystalline lattice. Salt feels solid because electromagnetic attraction between ions resists any separating force. Though no actual contact occurs and forces alone maintain structure. Metallic bonds work differently. Electrons become delocalized in metals, shared not between atom pairs, but across the entire material. This electron sea flows around positive metal ions, providing the bond holding metal together, while also explaining why metals conduct electricity and heat so well, since shared electrons move freely in response to applied fields or temperature gradients. Van der Waals forces, much weaker than chemical bonds, arise from momentary fluctuations in electron distributions, creating temporary dipoles attracting neighboring atoms. These forces hold together graphite layers, allowing them to slide past each other, explaining why graphite works as lubricant, while diamond, with its covalent network, ranks among the hardest substances known. Same element, carbon, but different bonding, creates vastly different macroscopic properties. Each bonding type produces different degrees of apparent solidity, different resistances to deformation, different temperatures at which structure breaks down. Yet all arise from the same underlying physics: electromagnetic interactions between charged particles, constrained by quantum mechanical rules, operating across mostly empty space. Consider how this understanding applies to ordinary activities. When you walk across a floor, your feet do not touch it. Electron clouds of atoms in your shoes repel electron clouds of atoms in the floor surface, creating sufficient force to support your weight. You float above the floor by a fraction of a nanometer, held up by electromagnetic repulsion. Every step you have ever taken involved this levitation, and you have never touched the ground in any classical sense. Sitting in a chair means you do not rest on it, but hover above, suspended by the same electromagnetic forces. The compression you feel, the sense of chair pushing up against you, is electron clouds being compressed, with their mutual repulsion increasing as you try bringing them closer together. Picking up an object means your fingers do not grip it, but approach close enough that electromagnetic repulsion creates friction sufficient to lift the object against gravity. The sensation of holding something, of having control over it, emerges from forces acting across empty space between atoms that never touch. Eating food means you do not chew it in the sense of hard teeth crushing hard food. Both teeth and food are mostly empty space, and forces breaking food down are electromagnetic interactions between electron clouds, helped by mechanical advantage of jaw muscles, transmitting force through the emptiness-filled structure of bone. Every physical action works this way. Apparent contact, solid grip on reality, is always electromagnetic interaction across gaps that, relative to atomic dimensions, are vast. The world works as if solid because electromagnetic forces are so strong and consistent that the illusion is perfect at human scales. Understanding this does not change how you walk, sit, or eat, since forces remain the same whether you understand them or not. What changes is knowing what is actually happening, with the substrate of everyday life revealed as stranger and more subtle than intuition could have imagined. Modern technology exploits the quantum nature of matter in increasingly sophisticated ways. Transistors, building blocks of all digital electronics, work by controlling electron flow through semiconductor materials. A semiconductor has an energy gap between filled electron states and empty states above them, small enough that applying voltage can push electrons into conducting states. Manipulating electron behavior at quantum levels allows creating logic gates performing computation. Your smartphone contains billions of transistors, each a few nanometers in size, each exploiting quantum properties of electrons in silicon. Computational power, once requiring room-sized machines, now fits in your palm, because engineers learned controlling electron behavior at scales where quantum effects dominate. Magnetic storage in hard drives works by aligning magnetic moments of tiny regions on a disk. These moments arise from electron spin, a purely quantum mechanical property with no classical analog. When electrons in a region have spins aligned, the region becomes a tiny magnet pointing in one direction, and computer data is stored as patterns of these orientations, ones and zeros, encoded in quantum states. Medical imaging depends on quantum effects. MRI scans detect behavior of hydrogen nuclei in magnetic fields governed by quantum mechanical rules. CT scans use X-rays, photons produced by electron transitions in atoms, to image tissue density. Each technology exploits some aspect of quantum matter nature. Quantum tunneling represents another phenomenon impossible under classical physics. In classical terms, a particle lacking energy to overcome a barrier simply stops or bounces back. In quantum mechanics, particles have wave-like properties, with wave functions not stopping sharply at barriers, but decaying exponentially into them. If barriers are thin enough, wave functions can emerge on the other side, meaning particles have probability of appearing where they classically could not go. Tunneling is not rare or exotic, but essential to solar operation. Hydrogen nuclei in the solar core lack enough energy to overcome electromagnetic repulsion through classical means, meaning the sun should not shine. But quantum tunneling allows nuclei to pass through the repulsive barrier and approach close enough for strong nuclear force to bind them. Fusion proceeds, and the sun produces energy. The nature of touch deserves closer examination, because touch is the sense most directly associated with solidity. When skin contacts a surface, nerve endings respond to deformation. The deformation arises from electromagnetic repulsion between electron clouds in your skin and electron clouds in the surface. At no point do particles in your skin physically contact particles in the surface. The gap, though subatomic in scale, is real. What nerves detect is the force resulting from this repulsion. They cannot detect the gap because the gap is far below their resolution. They report pressure without reporting separation. The brain interprets this pressure as contact, as touch, as the solid reality of surface meeting surface. This interpretation served ancestors well. It allowed navigation of environment, manipulation of objects, detection of threats. The fact that contact was not actually contact made no difference. What mattered was the reliability of the sensation, its correlation with properties that did matter. The reliability remains. When you reach for an object, your hand stops at predictable distance. When you press against a wall, predictable resistance results. The forces creating these experiences are utterly reliable at human scales. You can build on them, literally, constructing entire civilizations of buildings and tools and machines, all resting on forces between particles that never touch. Different surfaces feel different because their electron cloud configurations differ. Smooth surfaces have uniform electromagnetic properties. Rough surfaces have irregular properties. Soft surfaces have electron clouds that compress easily. Hard surfaces have electron clouds that resist compression. All these properties report faithfully through sensation, even though what underlies them differs from what intuition expects. Temperature sensation also arises from electromagnetic interactions. Hot objects have atoms vibrating vigorously, and when skin approaches them, the vibrating atoms transfer energy to atoms in skin, raising their temperature, triggering heat-sensitive nerves. Cold objects absorb energy from skin atoms, lowering their temperature, triggering cold-sensitive nerves. The sensation is real. The mechanism involves forces across gaps, not contact between solid surfaces. Wetness is a more complex sensation, involving pressure, temperature, and surface tension effects. When water contacts skin, its molecules interact with skin molecules through electromagnetic forces. The distinctive sensation of wetness arises from the particular patterns of these interactions. Again, no traditional contact occurs. Molecules approach each other, forces operate, sensations result. Every tactile experience follows this pattern. The sensation is real and reliable. The physical process producing it is force interaction across empty space. The interpretation of contact between solid surfaces is incorrect in detail, while useful in practice. This matters philosophically because it separates experience from reality in a specific way. The experience is not illusory in the sense of being false or imaginary. It is illusory in the sense of being an interpretation that misrepresents underlying mechanisms while accurately representing practical properties. You can trust your sense of touch to tell you about surfaces, hardness, temperature, texture. You cannot trust it to tell you what matter is. The distinction extends to other senses. Vision reports colors that are brain interpretations of wavelength, not properties of objects themselves. Hearing reports sounds that are brain interpretations of pressure waves. Taste and smell report chemical interactions as qualities like sweet and fragrant. In every case, what we perceive is not raw reality, but processed interpretation. This processing is not a defect, it is how sensing works. Raw data at atomic and molecular scales would be meaningless to an organism. What matters is processed information that guides action. The processing necessarily transforms, simplifies, and interprets. Understanding this does not diminish sensory experience. Colors remain beautiful, music remains moving, food remains delicious. The knowledge that these experiences arise from processing rather than direct perception does not make them less real. As experiences, it makes them more interesting as phenomena. The same applies to solidity. Learning that touch is electromagnetic interaction rather than physical contact does not make the world feel less solid. The table still supports. The wall still resists. What changes is knowledge of why, not experience of what. This dual nature of understanding, changing what you know without changing what you feel, is characteristic of scientific knowledge about everyday phenomena. You know the Earth orbits the Sun, but the Sun still appears to rise and set. You know time dilates at high speeds, but time still feels uniform. You know matter is mostly empty, but matter still feels solid. Science adds a layer of understanding beneath the layer of experience. Both layers are real. Living with both is part of being scientifically literate in the modern world. Understanding atomic structure transforms how engineers and scientists approach problems. Materials engineering provides clear examples. Knowing that material properties arise from atomic arrangement allows predicting how changes in composition or structure will affect behavior. This is not guesswork, but calculation. The forces between atoms, the quantum rules constraining electron configurations, the ways crystals form and defects propagate, all can be modeled and predicted. Before this understanding, materials development was largely trial and error. Metallurgists mixed elements and tested the results. Some combinations worked better than others, but why remained mysterious. Understanding changed this. Now engineers can target specific properties by designing atomic arrangements to produce them. The semiconductor industry exemplifies this. Silicon is useful not because of some mysterious property, but because its electron structure allows controlled manipulation. Add certain impurities, and electrons flow more easily. Add others, and electron flow becomes harder. The transistor is not an invention of trial and error, but of deliberate design based on understanding of how electrons behave in crystal lattices. Medical applications follow similar logic. Drug molecules work by fitting into receptor sites on proteins, and this fitting is electromagnetic interaction between electron clouds. Understanding this allows designing drugs that fit specific receptors, targeting diseases rather than affecting the body broadly. The lock and key model of drug-receptor interaction is a model of electron cloud compatibility. Nanotechnology represents the frontier of this approach. Building structures atom by atom or molecule by molecule, taking advantage of quantum effects rather than fighting them, creating materials with properties impossible at larger scales, all depend on deep understanding of what matter is and how it behaves. The contrast with pre-scientific understanding is stark. Ancient metallurgists could make bronze without knowing about atoms. Modern materials scientists design new alloys from first principles without ever making them until the design is complete. The understanding is not just philosophical, but practical, enabling capabilities that would otherwise be impossible. This has implications for education and public understanding. Science education that presents atoms as tiny balls fails to convey the actual nature of matter. It perpetuates the intuitive picture that atomic physics has disproved. Better education would start with the strangeness, with the emptiness, and the forces, and the quantum rules, even if this is harder to explain. The difficulty of explanation is real. Quantum mechanics is counterintuitive. Probability and superposition and exclusion do not match everyday experience. Teaching these concepts requires accepting that intuition will be violated. The reward is understanding that goes deeper than any intuitive picture could. Public understanding matters because technology increasingly depends on quantum effects. Policy decisions about technology require some grasp of underlying physics. Citizens who understand that matter is mostly empty space, that solidity is electromagnetic interaction, that quantum rules govern atomic behavior, are better equipped to evaluate claims and decisions involving these phenomena. This is not to say everyone must become a physicist, but basic literacy about what matter is, what solidity means, how atoms work, is part of being educated in the modern world. The knowledge is accessible to anyone willing to let go of intuitive pictures and accept strange truths. The strangeness does not diminish over time. I have worked with these concepts for years, and they remain counterintuitive. The table still looks solid. The hand still feels substantial. Understanding does not change perception. But the understanding is there, underlying perception, adding depth to experience, revealing the remarkable nature of what seems ordinary. Materials science exploits knowledge of atomic structure to create materials with desired properties. Understanding that solidity arises from electromagnetic forces and quantum exclusion allows predicting how new materials will behave. Know the atomic structure, and you can calculate electronic configuration. From electronic configuration, predict mechanical, electrical, thermal, and optical properties. Materials can be designed on paper before synthesis in laboratories. Steel demonstrates this with iron alloyed with carbon and other elements, where carbon atoms fit into gaps in iron lattice, distorting it in ways increasing hardness. Different amounts and types of alloying elements produce steels ranging from soft and ductile to hard and brittle. Carbon fiber reinforced plastic combines strong carbon fibers with polymer matrix, where neither component alone has the composite's properties. Fibers provide strength along their length, while matrix transfers loads between fibers and prevents buckling, yielding material stronger and lighter than either component. Nanomaterials engineer properties at atomic scales. Carbon nanotubes are cylindrical arrangements of carbon atoms extraordinarily strong for their weight. Graphene, a single carbon atom layer in hexagonal lattice, shows remarkable electrical conductivity and mechanical strength. These materials exist because scientists understand atomic bonding well enough to create new arrangements with new properties. When materials deform under stress, atomic-level picture reveals what happens. Elastic deformation occurs when stress pushes atoms slightly from equilibrium positions, with electromagnetic forces between them increasing and storing energy like compressed springs. Remove stress, and atoms return to original positions with stored energy released. Metals, bent slightly within elastic range, spring back, and rubber, stretched and released, returns to original length. Plastic deformation occurs when stress exceeds elastic limit. Atoms are forced past positions from which they can return, and, in metals, this involves atoms sliding along crystalline planes, reorganizing into new, stable configurations. Bending a paperclip back and forth causes plastic deformation as atomic planes slide and find new positions. The clip does not spring back because atoms have found new equilibrium positions. Knowing you are mostly empty space raises interesting questions about identity and continuity. Atoms composing your body are not the same atoms that composed it years ago. You continuously take in new matter through food and air, incorporate it into tissues, and release old matter as waste and exhaled gases. The material you is constantly turning over, replaced bit by bit, while you remain recognizably yourself. What then is you? Not specific atoms, since those change. Not solid continuous substance, since that does not exist. What persists is a pattern, a configuration of electromagnetic forces and quantum states maintaining itself through constant matter exchange. You are more like a wave than a thing. Ocean waves consist of water molecules, but no molecule travels with the wave. The wave is a pattern of motion passing through matter, not the matter itself. Similarly, you are a pattern of organization passing through atoms, not the atoms themselves. This does not diminish your reality because patterns are real with real causal powers. Waves knock you down. Hurricanes destroy cities. You are a remarkably stable, self-maintaining pattern persisting for your entire life, while material substrate has turned over many times. Your existence depends on the very emptiness that seems to undermine common-sense notions of what you are. If atoms were solid, if matter were continuous, the chemistry of life could not work. Electrons could not be shared in bonds. Molecules could not form. Cells could not function. Our ancestors did not need understanding atoms to survive, but needed navigating environments filled with objects that could help or harm them. Evolution optimized senses for survival utility, not physical accuracy. Consider what accurate atomic perception would require. Sensing individual atoms approximately 0.1 nanometers in size, when nerve cells are roughly 10,000 times larger. Tracking electrons moving at thousands of kilometers per second. Somehow perceiving probability distributions and quantum states, having no analog in macroscopic experience. Such perception would be computationally overwhelming and practically useless. Evolution produced a shortcut. Instead of perceiving atomic structure, we perceive macroscopic properties correlating with atomic structure in consistent ways. Hardness, softness, roughness, smoothness, temperature, flexibility. Compressed representations of complex atomic realities giving enough information to interact effectively without requiring quantum mechanical calculations. The illusion of solidity extends to all senses, not just touch. Vision perceives solid objects because light interacts with electron clouds in characteristic ways. When light strikes a surface, some wavelengths are absorbed, while exciting electrons to higher energy states. Other wavelengths reflect, bouncing off electron clouds, and wavelengths reaching your eyes determine perceived color. A red apple is red because its surface electrons absorb most wavelengths while reflecting those corresponding to red. Glass is transparent because energy gaps in its electronic structure do not match visible light frequencies. Ultraviolet light is absorbed, which is why glass blocks UV. But visible light has the wrong frequency to be absorbed, so it passes through. The same material can be opaque to some frequencies and transparent to others, depending entirely on electron energy levels. Metals are opaque because delocalized electrons absorb light across a wide frequency range, oscillating and rapidly re-emitting energy to produce reflection. Polished metal's shiny appearance is electrons bouncing light back. Hearing involves pressure waves traveling through matter. Sound in air consists of compressions and rarefactions, regions where air molecules are pushed closer or pulled apart. When sound reaches your ear, pressure variations vibrate your eardrum. The force felt is, at atomic level, electromagnetic interaction with air molecules pushing against it. You hear because electron clouds transfer momentum to other electron clouds. Taste and smell involve molecules binding to receptors in mouth and nose. These binding events are chemical, involving electron sharing and electromagnetic attraction. Salt's flavor, coffee's aroma, sweetness sensation all arise from electrons interacting according to quantum mechanical rules. When a sugar molecule binds to a taste receptor, electron clouds are finding compatible configurations, not hard objects locking together. Every sensory experience ultimately reduces to electromagnetic interactions between electron clouds. The five senses are five different ways of detecting and interpreting these interactions. The rich, varied world of experience is your brain's interpretation of force field patterns at scales you cannot directly perceive. Surfaces we interact with daily deserve closer examination. Intuitively, a surface is where an object ends and empty space begins, a sharp boundary between substance and nothing. At atomic level, no such sharp boundary exists. Atoms at a solid surface simply have fewer neighbors, with electron clouds extending into empty space with probability distributions never going exactly to zero. When you touch a surface, your finger's electron clouds approach the surface's electron clouds. At some separation, electromagnetic repulsion becomes strong enough that you perceive resistance, with this separation depending on atoms involved, their electronic configurations, and the force you apply. Surface texture, what we perceive as smooth or rough, arises from atomic arrangements at the boundary. Polished metal has atoms in relatively regular patterns producing uniform electromagnetic properties across the surface. Your finger encounters consistent resistance at consistent separation, and the result feels smooth. Rough surfaces have atoms arranged irregularly, with peaks and valleys at atomic scale. So your finger encounters varying resistance at varying positions, producing textured sensation. Friction between surfaces arises from electron cloud interaction. When surfaces slide past each other, electron clouds must rearrange as different atoms pass. This rearrangement requires energy, perceived as resistance to sliding. Static friction, the force needed to start motion, typically exceeds kinetic friction because surfaces have had time to settle into lower energy configurations that must be disrupted. Lubricants put something between surfaces, reducing electron-cloud interactions. Oil molecules slide past each other more easily than metal atoms do. So, coating surfaces with oil reduces energy. Cost of relative motion. Surfaces are not actually touching, with or without lubricant. The lubricant simply changes electromagnetic landscape between them. When you squeeze a rubber ball, your fingers exert force on the surface, transmitting through rubber and pushing atoms closer throughout the material. Electron clouds compress, approaching each other more closely than relaxed state, storing energy because atoms want returning to equilibrium positions. Release the ball, and stored energy drives expansion, with electron clouds pushing apart and atoms returning to preferred separations. Density provides another perspective on atomic emptiness. Materials vary enormously in density. Lead at roughly 11 grams per cubic centimetre, aluminum at about 2.7, styrofoam at perhaps 0.05. We perceive these differences as differences in heaviness for the same volume. What determines density depends at atomic level on two factors: how heavy individual atoms are and how tightly they pack together. Lead atoms are much heavier than the aluminum atoms, containing more protons and neutrons, and they also pack relatively tightly in crystalline structure. Even the densest naturally occurring material, osmium, at about 22.6 grams per cubic centimetre, is mostly empty at atomic level. Atoms are heavy, with many nucleons. They pack efficiently, but each atom remains as empty as any other, with its tiny nucleus and distant electron clouds. Heaviness you feel when lifting dense material is gravitational attraction to all those atomic nuclei. More nucleons mean more mass, more gravitational pull, more effort to lift. The sensation of heaviness is real. The solid substance your intuition imagines causing that heaviness is not. The distinction between matter and empty space becomes stranger when considering antimatter. For every matter particle type, an antimatter counterpart exists. Electrons have positrons, identical in mass but opposite in charge. Protons have antiprotons. Neutrons have antineutrons. These antiparticles are real, produced in laboratories and observed in cosmic rays. When matter and antimatter meet, they annihilate, converting entirely into energy. An electron meeting a positron produces gamma-ray photons, carrying away all the energy that was combined mass of particles. Nothing solid remains. What seemed like substance was actually convertible to radiation. This convertibility reveals that matter is not a fundamental category separate from energy, but a form of energy, mass being equivalent through Einstein's equation. Solid matter you touch could, under right circumstances, become pure radiation with no particle content. Particles are excitations of quantum fields, and annihilation is two field excitations cancelling out, with energy redistributed to electromagnetic field as photons. Questions remain about the nature of matter that current physics cannot fully answer. We do not know why the Pauli Exclusion Principle holds. We can state it precisely, apply it successfully, and observe its consequences everywhere from atomic spectra to neutron stars. But we cannot explain why fermions obey this rule while bosons do not. It appears to be a fundamental fact about how reality works, accepted because observation confirms it, not because we understand some deeper reason for it. We do not fully understand how quantum mechanics connects to classical physics. At small scales, quantum effects dominate. At large scales, classical physics provides excellent approximations. The transition between these regimes, the question of why large objects do not exhibit obvious quantum behavior, remains an area of active research. We do not know whether quantum field theory is the final word on matter's nature. It predicts experimental results with extraordinary precision, but it does not incorporate gravity in a fully consistent way. Attempts to unify quantum field theory with general relativity suggest our current understanding may be an approximation valid only at scales we have probed, with different physics emerging at smaller distances or higher energies. The emptiness of atoms raises questions about what space itself is. Fields permeate that emptiness, and the vacuum state of quantum fields is what fills it. But what is the vacuum? It appears to have energy and structure, and it is not nothing in any classical sense. The nature of quantum vacuum remains one of physics' deep mysteries. These questions do not undermine conclusions we have drawn. Matter being mostly empty, solidity being an emergent illusion, forces rather than contact producing resistance, all of this is established beyond reasonable doubt. Remaining questions concern deeper levels of understanding, not whether the current picture is correct, but what explains it. What does this understanding give us beyond intellectual satisfaction? It gives us technology. Semiconductors, lasers, nuclear power, atomic clocks, all depend on quantum mechanical understanding of matter. Transistors in every electronic device exploit quantum properties of electrons in solids. GPS satellite precision requires accounting for atomic scale physics. Understanding what matter actually is, not what intuition claims, has transformed civilization. It gives us medicine. Imaging techniques peering inside the body without cutting depend on how atoms respond to radiation and magnetic fields. Drug design increasingly relies on understanding molecular interactions at quantum level. The same principles explaining why your hand cannot pass through a table also explain why certain molecules bind to certain receptors. It gives us materials. Understanding atomic structure allows designing materials with properties that never existed naturally. Superconductors, metamaterials, graphene all emerged from detailed knowledge of how atoms arrange and interact. The illusion of solidity, once understood, becomes tool for engineering new illusions with desired properties. It gives us perspective. Knowing you are mostly empty space changes nothing about experience and everything about your place in the universe of understanding. You are built from the same principles governing stars and semiconductor chips. Forces holding your body together are the same forces producing lightning, binding molecules, and creating the northern lights. Understanding reveals connection. This perspective also brings humility. Certainty you feel when touching a solid surface is, at fundamental level, a misrepresentation of what is happening. Your senses, evolved for survival rather than truth, report confidently on matters they cannot directly perceive. The reminder that experience can be simultaneously useful and misleading extends far beyond physics into a lesson about the limits of intuition in all domains. Crystalline structures provide a beautiful example of how atomic arrangement produces macroscopic properties. In a crystal, atoms or molecules arrange themselves in regular, repeating patterns, not imposed from outside, but emerging spontaneously because certain arrangements minimize energy. When molten metal cools, atoms settle into positions minimizing electromagnetic repulsion with neighbors while maximizing attraction, resulting in a lattice, a three-dimensional grid of atoms at precise intervals. Different elements and compounds form different lattice structures depending on their bonding. Iron atoms at room temperature arrange in a body-centered cubic structure, each atom surrounded by 8 nearest neighbors at cube corners. Crystal facets reflect internal atomic symmetry, with flat faces corresponding to planes of atoms in the lattice. Beautiful geometry of snowflakes reflects hexagonal symmetry of ice crystal lattices. External appearance emerges from invisible atomic arrangement. Solidity is what physicists call an emergent property, and understanding emergence clarifies why the illusion is so complete. Emergence occurs when systems display properties their components do not possess individually. A single water molecule is not wet. Wetness emerges only when enormous numbers of water molecules interact. A single neuron is not conscious. Consciousness emerges from interaction of billions of neurons. Emergence is ubiquitous. Most properties we care about in everyday life are emergent. Solidity is emergent in this sense. A single atom is not solid, having no surface, no rigidity, no ability to resist penetration. It is a nucleus surrounded by probability clouds. Place trillions of these atoms together, each repelling neighbors through electromagnetic forces and quantum exclusion, and solidity emerges. Collective behavior of empty atoms produces the experience of solid matter. Once you recognize emergence, solidity becomes less mysterious. The question is not why empty atoms feel solid, but what collective behaviors produce the emergent property of solidity. The answer is electromagnetic. Repulsion and quantum exclusion acting across trillions of atoms simultaneously. Emergent properties are real, even though they exist only at collective levels. Wetness is real, even though no single molecule is wet. Solidity is real, even though no single atom is solid. Properties are patterns in how systems behave, not intrinsic features of components. Exotic quantum states of matter push the illusion of solidity in strange directions. Superconductivity occurs when certain materials are cooled below critical temperatures. Electrical resistance vanishes completely, and current flows without energy loss, continuing indefinitely without applied voltage. This seems to contradict everyday experience, where wires always resist current, at least slightly. The explanation involves electrons pairing up in ways bypassing normal scattering processes. In ordinary conductors, electrons bounce off atomic vibrations, losing energy as heat. In superconductors, electron pairs move through material without scattering. The emptiness of atoms, normally responsible for forces impeding electron flow, becomes irrelevant to paired electrons. Superfluidity is another exotic state. Liquid helium, cooled below about 2 Kelvin, becomes superfluid, flowing without viscosity. It creeps up container walls and passes through tiny holes ordinary liquids cannot penetrate. Normal fluid properties, arising from atomic interactions, vanish. Both phenomena demonstrate that emergent properties of matter are not fixed. Under different conditions, the same atoms produce radically different macroscopic behaviors. Solidity and resistance experienced at room temperature are not fundamental, but emergent properties, alterable by changing conditions. Atomic emptiness, underlying matter, has profound implications for biology. Every biological process operates through the same forces, creating the illusion of solidity. When a muscle contracts, protein molecules slide past each other with electron clouds, interacting through electromagnetic forces. When nerves conduct signals, ions flow through channels with passage governed by electromagnetic attraction and repulsion. When DNA replicates, molecules bind and unbind, finding partners through electronic complementarity. Complexity of life emerges from electromagnetic interactions in mostly empty atomic structures. A cell is a bag of mostly empty atoms organized into functional units. Each unit a structure of mostly empty atoms arranged to perform specific chemical operations. The bacterium, the brain cell, the beating heart, all empty space configured to produce particular behaviors. This perspective helps explain why life is both resilient and fragile. Electromagnetic forces creating biological structure are strong enough to maintain organization against many disturbances. Cells repair damage. Organisms heal wounds. Ecosystems recover from disruptions. Forces holding life together are robust. Yet life is fragile to disturbances disrupting the right configurations. Radiation damages DNA by ionizing atoms, altering electromagnetic environment. Poisons interfere with enzymatic function by binding where they should not. Temperature extremes denature proteins, destroying precise folding, making them functional. Electromagnetic organization that is life can be scrambled by the right interventions. The dual nature of biological matter, simultaneously resilient and fragile, follows from its being patterns of force in empty space. Patterns can persist through many changes while remaining vulnerable to disruptions attacking their organizing principles. Your body is a triumph of electromagnetic organization. Trillions of cells, each containing billions of molecules, each molecule comprising atoms that are themselves nearly empty, all working in coordination to produce you. Solidity you feel when touching your own skin is the solidity of life. Force patterns in emptiness, remarkably stable, yet entirely dependent on continuation of quantum mechanical rules sustaining them. Consider complex molecules like DNA, and how consequences of quantum exclusion play out across thousands of atoms. Every bond, every fold, every interaction allowing DNA to encode genetic information follows from electrons obeying the rule that they cannot share quantum states. The instruction set for life is written in the language of Pauli exclusion. Hydrogen bonds, weaker than covalent bonds, hold DNA's double helix together and allow it to unzip for replication. Enzymes have precisely shaped active sites where substrates fit. And this lock and key specificity arises from how electron clouds of enzyme and substrate interact. Proteins fold into functional shapes because their amino acid sequences create particular patterns of electromagnetic attraction and repulsion. All of biochemistry operates through forces across empty atomic space. Consider your own body with this perspective. If you could somehow see atoms composing your hand at stadium scale, you would see countless tiny beads suspended in vast empty spaces, each bead separated from neighbors by tremendous distances relative to its size. The image would look nothing like solid flesh. It would look like scattered particles floating in immense void, held in position by invisible forces. Yet, when you look at your hand, you see continuous surface, solid form, unbroken matter. The illusion is complete and utterly convincing. Before we continue, try holding that image in your mind. Everything you perceive as solid, every wall, every rock, every person, is constructed from these stadium-sized atoms with their marble-sized nuclei. Solidity you experience emerges from forces operating across that emptiness, not from anything physically filling the space. Think about what this means for your own body. You are built from atoms. Those atoms are almost entirely empty. The solid, continuous surface you perceive when looking at your hand is a macroscopic illusion created by forces operating in a region that is volumetrically almost pure emptiness. Discrepancy between perception and reality only matters when you venture beyond everyday scales. At atomic level, intuitive physics fails completely. Quantum effects dominate. Probabilities replace certainties, and familiar concepts like position and trajectory become meaningless. Our intuitions were not evolved for that regime and do not work there. The vacuum itself, what we casually call empty space, is not classical emptiness. It is the vacuum state of quantum fields, the lowest energy configuration of all fields permeating reality. When you look at emptiness within an atom, you are looking at something similar. The space between nucleus and electron is not classical void. It is quantum vacuum, populated by electrons' probability distribution and permeated by electromagnetic fields. Emptiness has structure, even though it lacks substance. This perspective helps clarify why atoms are mostly empty. They are not empty in the sense of containing nothing. They are empty of solid matter, while full of fields and probabilities. The distinction matters because fields and probabilities are real things with real effects. The electron is genuinely present in the orbital region, even though it is not there as a localized particle. The universe as a whole is similarly full while seeming empty. Space between galaxies contains the same quantum fields existing inside atoms. It contains magnetic fields left over from early cosmic history. It contains radiation, photons traveling from distant sources. Apparent emptiness is an illusion of scale, much as apparent solidity of matter is an illusion of scale. What we perceive as stuff of the universe, solid matter we can touch and manipulate, is a thin excitation riding atop an ocean of quantum fields. The excitations are real, but they are not all there is. The fields themselves are equally real and far more pervasive. This is the part that still amazes me. The feeling of pressing against something rigid, something immovable, is produced entirely by electromagnetic fields interacting across a void. There is no rigid object in traditional sense. There is only force, and that force happens to be strong enough to create the complete illusion of rigidity. Every object you interact with daily embodies this quantum reality without revealing it. The chair supporting you right now maintains your weight through electromagnetic repulsion between electron clouds in the chair and electron clouds in your body. No part of you touches any part of the chair in classical sense. Forces interact across gaps that, at atomic scales, are immense relative to nuclei involved. The floor beneath the chair supports both you and the chair through the same mechanism. Building's foundation presses against ground, ground presses against bedrock, and all of it is force fields in configurations of relative stability. Entire structural integrity of every building ever constructed depends on electrons refusing to share quantum states with other electrons trying to occupy the same space. The keyboard used to write this script, the screen displaying these words, the device producing these sounds or images, all operating through the same electromagnetic forces and quantum rules. Silicon chips work because electrons in semiconductors follow quantum mechanical laws. Light from your screen results from electrons transitioning between energy levels. Every aspect of modern technology exploits these principles. What changes when you learn this is not the objects themselves, but your understanding of what objects are. The chair remains supportive. The floor remains stable. Nothing about their function changes. What changes is realization that function emerges from something radically different than naive intuition suggests. Think about this the next time you pick up a cup of coffee. The cup feels solid, rigid, capable of holding liquid. The liquid inside feels continuous, flowing, wet against your lips when you drink. Every sensation you experience arises from quantum field excitations interacting through electromagnetic forces across mostly empty space. The coffee, the cup, your lips, your hand, all constructed from this same underlying reality, all producing sensations that seem to report solid substance when the substance is an emergent phenomenon, not a fundamental feature. Scanning tunneling microscopes and atomic force microscopes have given us direct views of atoms. These instruments do not see atoms the way eyes see objects. They map forces, currents, interactions at atomic scales. What they reveal is a landscape of probability and force, not a collection of tiny, solid objects. When an AFM tip approaches a surface too closely, the force increases dramatically. This is Pauli repulsion in action. The microscope literally feels atoms pushing back, and the image it produces is a map of that resistance. The abstract principle becomes visible, converted to pictures showing individual atoms as bumps and ridges. These images have become so common that we sometimes forget how remarkable they are. Humans, using instruments and ingenuity, have learned to see the invisible architecture of matter. We have confirmed that atoms are real, that they behave as quantum mechanics predicts, that the solidity we experience emerges from their collective interactions. The confirmation extends across chemistry, physics, materials, science, and biology. Every field touching atomic structure has verified the picture. Atoms are mostly empty. Forces create apparent solidity. Quantum rules govern everything at small scales. This convergence of evidence from independent directions makes the conclusion as certain as science gets. We are not guessing about atomic structure. We have probed it from every angle, with every technique, and found the same underlying reality. The certainty does not diminish the strangeness. Matter remains counterintuitive no matter how much evidence accumulates. The brain evolved in a world of solid-seeming objects and cannot truly internalize that those objects are mostly empty space. Understanding sits alongside intuition without displacing it. Perhaps this is the most important lesson. Reality exceeds intuition. What feels certain and obvious may be, at a deeper level, entirely wrong. The humility this suggests extends far beyond physics. In any domain, the comfortable picture might be incomplete. The familiar might hide the strange. Matter being mostly empty space is just one example. Time flowing at a uniform rate everywhere is another intuition that turns out wrong. Space being flat and Euclidean is another. The universe having existed forever is another. Science keeps finding that common sense, however useful, is not a reliable guide to deep truth. The value of this discovery is not just technical. It is a reminder of human intellectual reach. We are made of matter that hides its own nature. We evolved senses that report solidity where emptiness exists. Yet, we figured it out anyway. Reason and investigation revealed what perception concealed. That achievement belongs to all of humanity. The specific discoveries came from Rutherford, Pauli, Heisenberg, and many others. But the capacity for discovery is broadly human. Anyone can understand what matter is. Anyone can appreciate the ingenuity that revealed it. The knowledge is a shared inheritance. When I first learned this, I found it both humbling and liberating. Humbling because it revealed how much of reality lies beyond direct perception. Liberating because it demonstrated how much we can learn through careful investigation despite our sensory limitations. The certainty you feel when touching a solid surface is, at a fundamental level, a misrepresentation of what is happening. Your senses, evolved for survival rather than truth, report confidently on matters they cannot directly perceive. Reminder that experience can be simultaneously useful and misleading extends far beyond physics into a lesson about limits of intuition in all domains. Consider more carefully what accuracy would require if our senses could perceive atomic structure. You would need resolution billions of times finer than what eyes provide. You would need timing fast enough to track particles moving at significant fractions of light speed. You would need somehow to perceive superposition and probability rather than definite position and trajectory. No biological sensor could achieve this. No neural architecture could process the information. Evolution could not have produced such perception, because the computational resources required would exceed what any organism could maintain. The shortcut was not just convenient, but necessary. The shortcut defines what we are. We are beings who experience the world as solid, continuous, substantial. We walk on floors, sit in chairs, hold objects, all without any hint of atomic emptiness. The sensation of reality, the feeling that we are in contact with something real and solid, is genuine, even though its interpretation is mistaken. This creates an interesting philosophical situation. The experience of solidity is not an illusion in the sense of being imaginary. It is an illusion in the sense of being a simplified representation of something more complex. The simplification is so thorough that it hides the underlying reality entirely. You cannot detect the emptiness through sensation. Only through measurement and inference can you discover it. In this sense, discovering atomic structure was like discovering a hidden room in a familiar house. The house looked complete. Nothing suggested anything was missing. Yet there was more to it than appearance revealed. The discovery did not change the house, but changed understanding of what the house contains. Your body is like that house. It appears complete, solid, continuous. Nothing in sensation suggests emptiness or quantum effects. Yet those features are there, underlying everything, constituting the actual structure of what you are. Discovery does not change your body, but changes understanding of what your body is. The analogy extends to the entire physical world. Everything visible, tangible, audible, operates through the same underlying physics. Everything that seems solid is mostly empty. Everything that seems to touch is interacting through forces across gaps. The familiar world sits atop a stranger one, and we live in both simultaneously, perceiving the familiar while inhabiting the strange. This dual existence characterizes the human situation with respect to physics. We evolved for one level of description and have discovered another. We live day to day with intuitive physics while knowing that intuitive physics is incomplete. The knowing does not change the living. We still walk on floors, still feel solidity, still experience the world as our senses present it. What the knowing adds is perspective. The table that seems so ordinary, so solid, so simply what it appears, is actually a remarkable configuration of forces across emptiness. The hand that touches it is equally remarkable. The contact that seems so straightforward never actually occurs. Understanding adds layers of meaning to everyday experience without changing the experience itself. Some might find this disturbing. If matter is not what it seems, if solidity is illusion, what can we trust? The concern, though understandable, misses the point. The forces are real. The atoms are real. The configurations creating apparent solidity are real. What is not real is the naive picture of solid lumps of substance filling space. That picture was never accurate. Discovering its inaccuracy does not remove anything from reality. It adds to understanding of what reality is. The forces holding your chair together are no less reliable for being understood. The floor beneath your feet is no less supportive for being mostly empty space. The world works. Understanding why it works does not make it work any less. If anything, understanding increases appreciation. The fact that forces can create such convincing illusion, that empty atoms can form solid-seeming matter, that quantum rules can produce the classical world we inhabit, is remarkable. The world is more interesting for being understood, not less. The discovery that solidity is an illusion carries philosophical implications worth considering. It challenges naive realism, the intuitive view that the world is roughly as our senses present it. Your senses report solid, continuous, substantial matter. The world is actually mostly empty space, permeated by forces and fields. The sensory report is not wrong exactly, but fundamentally incomplete. What you perceive is a dramatically simplified summary of something far more complex and strange. This does not mean the external world is illusory. The atoms are real, the forces are real, the emptiness is real. What is illusory is the interpretation your brain constructs from sensory data. The sense that you are dealing with solid substance when actually dealing with force fields in configured emptiness. The discovery also illustrates the gap between intuition and truth. Human intuitions were shaped by evolution for survival, not for accuracy about deep physics. The intuition that matter is solid served ancestors well, helping them navigate the world, avoid dangers, exploit resources. That the intuition is fundamentally mistaken about what matter is did not matter for survival. Science repeatedly finds intuitive pictures wrong. Earth feels flat, but is round. Time feels absolute, but varies with velocity and gravity. Matter feels solid, but is mostly empty. The pattern suggests humility about other intuitions. Where else might common sense be radically mistaken? The discovery reveals the power of investigation. Humans, using instruments and mathematics, discovered truths about matter that no direct perception could reveal. We cannot see atomic emptiness or feel quantum exclusion. Yet we found these truths through careful reasoning from observations. Human capacity for understanding extends far beyond what biological senses directly perceive. Look around you and pick something you consider solid: a wall, a book, your own hand. Try holding in your mind what we have discussed. That object is constructed from atoms. Each atom has a nucleus, roughly 100,000 times smaller in diameter than the atom itself. Electrons occupy immense relative distances, their positions described by probability distributions rather than fixed locations. Space between nucleus and electron clouds is not empty in classical sense, but contains electromagnetic fields and quantum wave functions. When you touch that object, nothing in traditional sense of physical contact occurs. Electron clouds in your hand approach electron clouds in the object. Electromagnetic repulsion pushes back. Pauli Exclusion Principle prevents electrons from sharing quantum states, adding powerful resistance to any overlap. These forces, operating across empty spaces within atoms, create the sensation of solidity you experience. The object is real. Matter composing it exists. But the hard, continuous, space-filling substance your intuition reports is emergent property, not fundamental feature. What is fundamental is fields, forces, quantum rules. Does it feel different, knowing what you now know? Or does the illusion persist as complete as ever, your senses unchanged by understanding? For most people, the illusion persists. The wall still looks solid, the hand still feels substantial. Understanding does not override perception. But something shifts in how you relate to that perception. You know something your senses do not report. You see through the illusion, even while experiencing it. That dual awareness, knowing and perceiving simultaneously, is what scientific understanding offers. Perspective shifts help appreciate what atomic emptiness means. If you could shrink yourself to electron size and sit on a hydrogen atom's nucleus looking out at the electron, what would you see? At that scale, the electron's orbital extends roughly 50,000 times the nucleus diameter in every direction. If the nucleus were a golf ball, the electron would orbit somewhere within a sphere about 1.5 kilometers, nearly a mile in radius. The electron itself would not be a tiny ball you could see. It would be a probability distribution, a cloud of possibility spread across that enormous volume. You could not point to where the electron is because it does not have a definite position. It is everywhere in the orbital with varying probability density. Imagine shrinking to proton size and looking around inside the nucleus. You would find other protons and neutrons held together by the strong nuclear force, immensely powerful, but acting only at extremely short range. Outside the nucleus, it has no effect. Inside, it overcomes electromagnetic repulsion between positively charged protons, binding them into stable nuclei. Zoom out to human scale, and this complexity vanishes into simple, apparent solidity. Unimaginable emptiness within atoms, probability clouds, nuclear forces, all average out into smooth, continuous matter of everyday experience. The scale of averaging is what creates the illusion. Consider how many atoms fit in a cubic centimeter of solid matter. Roughly 10 to the 22 atoms, 10,000 billion packed into a space about the size of a sugar cube. Each atom is mostly empty, but with that many atoms, their collective electromagnetic fields create a dense web of force, feeling utterly solid to human senses. The jump from atomic scale to human scale is comparable to the jump from bacterium to galaxy. We are describing phenomena so far beyond direct experience that analogy is the only tool available for understanding. Take the full volume of an atom and divide it into 1 million equal parts. That is 10 to the 18 identical tiny volume cells filling atomic space. Of those 10 to the 18 cells, how many would contain part of the nucleus? Approximately 1,000. Just 10 to the 3 of those million cells would contain any nuclear matter at all. The remaining cells, 999,999,999,999,000 of them, would be empty of any solid substance. They would contain only electromagnetic fields and quantum wave functions, force and probability, not substance. Consider what this means when objects appear to collide. A baseball striking a bat involves trillions upon trillions of atoms on each side. Each atom is hollow. The collision you see, the solid crack of bat meeting ball, is actually force fields deflecting force fields across vast, empty expanses. Nothing solid strikes anything solid. Fields interact, electrons repel, quantum rules enforce exclusion, and the macroscopic result is a home run. The baseball travels through air, itself made of atoms, itself mostly empty. Stadium full of spectators, grass on the field, light towers, night sky beyond, all constructed from this same emptiness, organized by force. The entire visible world is a pattern of interactions, not a collection of solid objects. Consider what we have learned about the nature of matter. Atoms are not tiny solid spheres. They are nuclei surrounded by probability clouds, with the nucleus occupying only a quadrillionth of atomic volume. The space between nucleus and electron clouds is not empty in classical sense, but filled with electromagnetic fields and quantum wave functions. What we perceive as solid matter is this emptiness, organized by force. The forces creating apparent solidity are electromagnetic repulsion between electron clouds and Pauli exclusion, preventing electrons from sharing quantum states. These forces operate across gaps that, at atomic scales, are vast relative to nuclear size. Nothing ever touches in the classical sense. All contact is force interaction across empty space. The discovery of this structure came through careful experiment and theory, from Rutherford's gold foil experiment showing that atoms have concentrated nuclei, through Pauli's Exclusion Principle explaining electronic structure, to modern AFM experiments directly measuring Pauli repulsion between atoms. Technology exploits this understanding. Transistors, medical imaging, new materials, all depend on knowing how atoms actually work. The illusion of solidity, once understood, becomes an engineering tool for creating new illusions with desired properties. Evolution produced senses that report solidity without revealing atomic structure. This served survival needs because atomic structure was irrelevant to survival, while macroscopic properties were everything. The shortcut works well for everyday life, while hiding the strange truth about what matter is. All senses operate through electromagnetic interactions between electron clouds. Touch is force detection. Vision is photon interaction with electrons. Hearing is pressure wave transmission through atomic structures. The rich world of sensory experience is brain interpretation of force patterns at scales too small to perceive directly. The philosophical implications include humility about intuition. The confident feeling that matter is solid turns out to be wrong about mechanism, while useful about outcome. This pattern, intuition being useful yet inaccurate, likely extends to other domains. Understanding does not change experience. The table still feels solid after you learn what solidity means. What changes is knowing, alongside feeling, the actual nature of what you touch. Dual awareness, perceiving while understanding, is what scientific literacy offers. The forces holding matter together are reliable. Buildings stand, tools work, bodies function. Understanding why does not make the reliability less. If anything, understanding reveals how remarkable reliability is, given that matter is mostly empty space held together by invisible forces. The next time you press your hand against a surface, you will feel solidity. You will also know that nothing is touching, that electron clouds are repelling, that forces create the sensation where no contact occurs. Both the feeling and the knowing are part of your experience. Together, they constitute understanding. This understanding is available to anyone willing to accept that intuition can be wrong, while experience remains real. The table is not what it seems, yet it is fully real. Both statements are true. Living with both is living with scientific understanding of matter. What does it mean to say matter is real, but solidity is an illusion? This distinction matters more than it might first appear. Matter is real. Atoms exist with measurable properties. They interact in predictable ways. Electron clouds, nuclei, forces between them, all as real as anything can be. You are made of matter, and that matter is not imaginary. Solidity, as traditionally conceived, meaning continuous substance filling space and resisting penetration through physical contact, is the illusion. What actually exists is localized concentrations of field excitations, separated by vast relative distances, interacting through forces creating the appearance of continuity and contact. The experience is real. The interpretation embedded in the word solid misrepresents what is happening. This distinction has practical implications beyond philosophy. Understanding that solidity arises from forces rather than physical substance helps explain phase transitions. Ice feels solid, water feels liquid, steam feels gaseous. In all three cases, you have the same water molecules. What changes is how strongly electromagnetic and quantum forces hold molecules in place. Solid, liquid, and gas are not fundamentally different matter types, but different arrangements of the same matter with different force balances. Understanding Pauli Exclusion's role helps explain why matter does not collapse. Without the exclusion principle, all electrons in an atom would drop to lowest energy state. Atoms would shrink dramatically. Matter as we know it could not exist. Structural rigidity of everything from diamonds to your bones depends on a quantum rule preventing electrons from piling into the same state. Understanding quantum field theory helps explain why particles can be created and destroyed. If particles were fundamental objects, creation from nothing would be mysterious. If particles are excitations of fields, creation is simply the field becoming excited. Annihilation is the excitation subsiding. Underlying fields remain. Specific excitations change. Each layer of understanding replaces a simpler picture with a more accurate one. The progression moves not toward greater confusion, but toward deeper coherence. The table you touch is not a fundamental feature of reality. It is one possible way quantum fields can be excited, a configuration happening to create the illusion of solid, stable, persistent substance. The configuration is real. The substance, as commonly understood, is not. Understanding why information appears so central to modern physics illuminates research direction. The vacuum catastrophe sits at the intersection of our two most powerful physical frameworks, quantum mechanics and general relativity. Wherever these frameworks meet, interesting things happen. Classical physics treats space as passive arena where things happen. Quantum mechanics reveals space is not passive, but seething with fluctuations. General relativity reveals space is not fixed, but dynamical, responding to energy and matter. Combining these insights produces tension. Quantum fluctuations carry energy. Dynamical spacetime responds to energy. Yet matter exists as mostly empty, mostly stable configurations. Something allows this stability. Newton's gravity united terrestrial and celestial mechanics. Einstein's relativity united space and time, matter and energy. Quantum mechanics united waves and particles. Each unification revealed unexpected connections and enabled unexpected applications. The next unification, whatever resolves remaining puzzles about matter, might reveal equally unexpected connections. We wait to discover what they are. When a solid object breaks, what actually happens at atomic level? Consider a glass window shattering. At impact, forces concentrate at certain points, stressing atomic bonds beyond their capacity. Covalent or ionic bonds holding atoms in fixed relationships snap, though not physically, of course, since no physical connection exists to snap. What breaks is the stable configuration of electromagnetic forces, with atoms held in proximity by attraction suddenly free to move apart. Cracks propagate through material at tremendous speed. Each broken bond releases stored energy, helping break neighboring bonds. A cascade spreads through glass in microseconds. And what was coherent solid becomes separate fragments. Each fragment still solid within itself, but no longer connected to others. The progression of human understanding on this topic follows a fascinating arc. For most of history, matter was assumed continuous. Ancient Greek philosophers proposed atoms, but speculation remained without experimental support. By the 19th century, chemistry provided strong evidence for atoms through regular proportions in chemical reactions suggesting discrete units combining in fixed ratios. The early 20th century brought discovery that atoms have structure. Thomson discovered the electron in 1897, proposing his plum pudding model. Rutherford's experiment demolished that picture and revealed nuclear structure. The mid-20th century brought quantum mechanics and quantum field theory, shifting understanding from particles as objects to particles as field excitations. Each step replaced intuitive pictures with counterintuitive but more accurate ones. Continuous matter gave way to atoms. Indivisible atoms gave way to nuclear structure. Particles gave way to fields. At each stage, the new picture seemed strange, even unbelievable, until evidence accumulated and understanding deepened. We are likely not at the end of this progression. Future discoveries may reveal quantum fields themselves are approximations to something deeper. String theory proposes one-dimensional strings as fundamental. Other approaches suggest different foundations. What seems fundamental today may prove composite tomorrow. The lesson from history is humility. The picture that feels obvious, that matches intuition, has repeatedly proven incomplete. We have covered considerable ground. We began with the sensation of pressing your hand against a table and asked what that sensation represents. The answer turned out far stranger than intuition suggests. Solidity is electromagnetic repulsion between electron clouds amplified by the Pauli Exclusion Principle. Nothing touches in classical sense. Forces interact across gaps that, relative to nuclear size, are enormous. Matter, composing everything you can see and touch, consists almost entirely of space filled with fields and wave functions rather than solid substance. Modern experiments using Atomic Force Microscopy directly observe forces at work, confirming Pauli repulsion is real and measurable. That abstract. Physics produces concrete effects. The illusion persists, though. You will continue experiencing solid objects as solid. Your senses will continue reporting continuous, substantial, space-filling matter where mostly empty space exists. Nothing learnt tonight changes how your nervous system processes pressure and reports resistance. What changes is understanding what those sensations represent. The wall is not solid the way it feels solid. Your body is not substantial the way it feels substantial. Everything you perceive as rigid, continuous material is an emergent phenomenon arising from forces operating across vast emptiness at scales your senses cannot detect. This is not diminishment of reality, but deepening of understanding. The chair supporting you is no less real for being made of mostly empty space held together by electromagnetic forces and quantum rules. If anything, it is more remarkable that fields and forces can conspire to create such convincing illusion of solidity, such stable and functional macroscopic reality. The bed you sleep in tonight will feel solid, the pillow soft but substantial, your body like a continuous, coherent thing pressing against the mattress. All of this electromagnetic forces and Pauli exclusion creating experience of substance where mostly emptiness exists. For all the emptiness within atoms, for all the absence of classical contact, the world works. Chairs support, floors hold, buildings stand. Bodies move through space and interact with environments in consistent, reliable ways. Forces creating the illusion of solidity are so robust, so stable, so powerful at human scales that we built civilizations on their effects without understanding their causes. Now you understand the causes. You know what feels solid is force fields interacting, electrons repelling, quantum rules enforcing exclusion. This knowledge does not diminish the experience, but enriches it. The next time you feel something solid, you can appreciate both the sensation and its source, marveling that forces alone, without any hard substance, can create such a complete and useful illusion. Thank you for joining me on this exploration of what matter actually is, and why what we experience as solid is fundamentally an illusion. If you found value in this, consider subscribing to help bring more explorations like this one to curious minds. Sleep well tonight, resting on a bed made of mostly empty space, held up by nothing but force. Good night.